This will be the 6th installment of my Digital Revolution video series. This time, we're going to talk about data compression, aka subsampling, and related topics such as points quantity and net digitizing frequency. If you missed episodes 1 through 5, check those out first before watching this one, especially videos 1 through 4. I'll leave a link up here. And when you're all caught up, meet me back here so we can level up those UT skills. In previous installments, we covered Nyquist theory and basic digitization principles. We discussed the relationship between digitization frequency and intervals and wave period and sampling rate and a lot of other stuff. We spoke about the importance of maintaining amplitude and timing fidelities. We also touched on the fact that in certain instances, the codes may give guidelines that pertain to these things. We discussed how an easy to remember relationship between digitization frequency, probe frequency, and sampling rate could help us in deciding which parameters should be used for different situations. The instrument's digitization frequency divided by your probe frequency will calculate the number of digital samples that you acquire per period, aka your sampling rate. We also said that you could simply multiply your probe frequency by the number of samples that you'd like to achieve per period, and that will tell you which digitization frequency at a minimum should be selected within your instrument settings. In the third video, we considered timing error and fidelity, which is how close a digital sample lands relative to the location of the peak at a worst-case scenario. This thought process is what helps us control our time of flight measurement accuracy, as well as the preservation of the frequency information of our signal. And then in the fourth video, we calculated amplitude fidelity, how closely the amplitude of the digital waveform represents the amplitude of that original analog, again at a worst case scenario. In each of these videos, we calculated several scenarios for each version of fidelity, so be sure to catch up on those for more information. During the timing fidelity discussion that we had in video 3, one of the scenarios we looked at involved acquiring a sampling rate of 5 samples per period. This is something that is sometimes referred to as ideal minimum sampling within our industry. We discussed that at the worst case scenario using this ideal minimum sampling, which always occurs when an analog peak is centered between 2 digital samples, the sample should be no further than 10% away from the peak location or position, essentially giving us at least 90% accuracy and 10% error potential. But remember, right now we're just talking about the horizontal position of the samples relative to the peak, not so much amplitude. This spacing helps control your measurement accuracy and your frequency preservation. This is timing fidelity, not so much amplitude fidelity. We'll have to think about a way to calculate that in a second. And then we also calculated just how far in inches and millimeters the samples may be from your peak for this situation. And again, we mentioned that 5 times your probe frequency, which gives you 5 samples per period, aka ideal minimum sampling, is the minimum digitization frequency allowed for encoded phased array in ASME Section 5, Article 4, Mandatory Appendix 5, and more on that in a minute. In video 4, we really got deep into the amplitude fidelity of a digital signal versus the original analog. Again, all those previous videos should be reviewed prior to this one. The installments in this series are meant to build upon each other. And again, we touched on the fact that the minimum digitization frequency allowed for encoded phased array in ASME is 5 times the probe frequency, which gives us 5 samples per period, aka ideal minimum sampling. And then we also worked out some of the math and science to prove why these things are important. Many of the phased array instruments on the market today use a fixed or a standard digitization frequency of 100 megahertz. That would be 20 times the frequency of a 5 meg probe, resulting in a sampling rate of 20 samples per period. Or 10 times the frequency of a 10 megahertz probe, resulting in a sampling rate of 10 samples per period. Or 44 samples per period with a 2.25 megahertz probe. So you get the idea, right? Other instruments actually use a higher digitization frequency. For example, the Sonatest Veo, which clocks in at 125 megahertz. But I'll keep this discussion based on 100 megahertz, as that's pretty typical in our industry. ASME Section 5, Article 4, Mandatory Appendix 5 deals with encoded phased array weld exams. This particular paragraph contains a very important, potentially confusing, sometimes controversial, and often overlooked statement. A-scan data shall be recorded in the area of interest in an unprocessed form with no thresholding at a minimum digitization rate of 5 times the examination frequency and recording increments of a maximum of 1 or 2 millimeters depending on your part thickness. Like I said a second ago, this paragraph is often overlooked or misunderstood. Everybody catches that bottom portion which deals with scanning resolution, but the words up top, that's a whole different story. And that's why we're having this discussion. And if I remember correctly, the ISO phased array codes actually require a digitization frequency of at least 6 times your probe frequency. So these parameters are mentioned throughout phased array and even TOFT codes worldwide. But for the sake of this discussion, I'll stick to ASME phased array. So as we said a couple slides ago, many of the phased array instruments on the market today use a fixed or a max digitization frequency of 100 megahertz. And again, that would be 20 times the frequency of a 5 meg probe or 10 times the frequency of a 10 meg probe, et cetera, et cetera. If you think about it, 20 megahertz would maybe be the highest frequency probe you could use and still get 5 samples per period. But that brings up another question. Are we just interested in the center frequency of the probe or the full spectrum of what that probe can produce and receive, maybe considering the bell curve bandwidth? That's worth thinking about. But for the sake of this discussion, we'll just simply focus on the center frequency of our probe. So based on the native digitization frequency of these instruments, one might think that they far exceed the code requirements when using your common probe frequencies. A benefit to using the full 100 megahertz digitization frequency to create our A-scans is that you'll have very high resolution signals as close to analog as digitally possible, providing excellent fidelity, which may be absolutely necessary for critical sizing tasks like corrosion, crack sizing, HTHA, where every thousandth of an inch or fraction of a millimeter of accuracy is important to your client. But the drawback is every sample occupies file space and every sample takes X amount of time to process and save. So with an increased number of saved samples, yeah, your A-scan quality is better, but your acquisition rate will be slower and your file size may be bigger. So this may prevent you from being very productive in the field, especially if you have a lot of welds to scan. Remember, ASME just says that at a minimum, we just need to digitize at least 5 times our probe frequency. So going way above that may sound great from a quality standpoint, but not necessarily from a production standpoint. Honestly, the norm in our industry is to just meet code requirements without going overboard and limiting our productivity. So what if we use a lower digitization frequency? What if our instrument would let us manually adjust this? Well, some instruments do and some don't. Well, if we did, our A-scan would not have as high of a resolution, but we would get an increase in scanning speed and have smaller data files. So signal quality may degrade just a little bit, but your production could be increased. But if we take our digitization frequency too low, we could incur a lot of error, as what we explored in previous videos. And there's always the chance that we may miss the peak amplitude of the signal. And if you choose too low of a digitization frequency, the problem will get even worse and you'll have even more error. And historically, we had another issue. Previous generation phased array instruments has slower processors and limited available file space for saving data. High resolution A-scans would often bog them down and make for slow scanning and limited productivity and limited maximum scan lengths. So here's an example on the storage situation. The maximum file size on the original OmniScan MX was only 160 megabytes. On the MX2, it was increased to 300 megabytes. And on the X3, you can go all the way up to 25 gigabytes. And also, as you can imagine, portable computer processing speed and data throughput has also drastically improved over the past 10 or 15 years. Some software allows you to choose a lower digitization frequency, which could help with scanning speed and file size. But if you're not careful, you could jeopardize the quality of your signal. So you have to know what you're doing. I'd recommend setting it to greater than or equal to 5 times your probe frequency, or whatever your code and procedure calls for. Many instruments use a smart compression feature to help reduce excessive A-scan samples. So for example, if you choose a compression of 4, the instrument would only record the most relevant or highest amplitude sample for every 4 points. That's a way of reducing file size and increasing scanning speed without losing any amplitude data. But although your amplitude information is preserved, it is possible to lose measurement accuracy along that A-scan time base, especially with excessive amounts of compression. This compression function is called different things in different software. On the Topaz and the X3 and I think the Gecko, it's simply called compression. On the MX2, it was called scale factor, and on the Sonotest Vaio, it's called subsampling, but it's all basically the same thing. Before we talk further about the smart compression that's used in many phased array instruments, let me first show you an example of maybe what you could call a not so smart compression, or just a simple downsampling. And to do that, we're going to analyze a few audio files. For this demonstration, I'm going to use an audio editing software called Audacity. What we're going to look at now are 2 audio files. Both of them are actually clips of the theme music at the beginning of this video. The first one, labeled high quality, is the original CD quality sound file, which was saved at a digitization frequency or sampling rate of 44,100 Hertz. This is also called 16-bit PCM audio. If you remember in video 2, we said that 20,000 Hertz is the upper end of the human hearing range. CD quality audio involves sampling at a rate just higher than that, just higher than the Nyquist minimum, to ensure that we preserve all the sound frequencies we need to hear. I will say this, in order to hear the differences between the sound quality in these 2 tracks, you may want to listen through a decent set of speakers or headphones. On the second one, I downsampled or compressed or subsampled the audio to a sampling frequency of 8,000 Hertz, well below the upper level of the audible frequency range. This will result in a poor listening experience and will lose many of the higher frequency tones that we would want to hear. So let's play the higher quality sample first, and then we'll follow it up with the low quality sample. And for this, just use your ears. And next, we'll play the lower quality sample. Now, something else I want to look at is this. I'm going to zoom in to the same point on both of these waveforms. And what you'll see, I have to zoom in a pretty good bit, but what you'll see, you see these dots showing up here? This low quality version is basically starting to pixelate because the space between these dots essentially represents the compressed version of this file where we actually took the sample. And you can see that the spacing between the dots, it's an equal spacing, right? There's an equal interval between dots. But if you look up here to the higher quality file, you'll see that the dots or the samples are much closer together. I've got to zoom in way further for them to pixelate. The distance between the dots is going to be indicative of the sampling rate, the quality of your digital capture. And then another thing to look at too that's also very interesting. You heard with your ears that we lost some of the high frequency content, but what I also want to look at is losing some of the amplitude information. So I'm going to zoom into this higher amplitude portion here, and we're going to look at some stuff. On these higher amplitude sections, let's just look at this waveform here of this high quality, right? So you can see where there was a high amplitude portion right here. But if you look directly down, there was no sample that was saved here in this spot. This kind of compression is going to just take whatever sample is available from this original waveform at this regular interval, right? So there's no guarantee that you're going to keep the max amplitude. This sort of compression, not only will you lose the high frequency components, but you'll also lose amplitude information because these samples are not saved in regard to a highest amplitude. They're just saved on a regular interval, and they will grab whatever sample of that original version was in that location. Okay, so what we're going to look at now is a comparison in the file sizes between the high quality and the low quality tracks that we just listened to. So the high quality that was recorded at 44,100 hertz, that one came in at 214 kilobytes. The one that I compressed to 8,000 hertz, the file size dropped to 60 kilobytes. So you can see there was a pretty dramatic reduction in file size. You could sort of equate this to phased array. If you're scanning with a higher digitization frequency, or what we'll talk about in a minute, if you're using a less compression, you're going to have a bigger file size, and it's actually going to take you longer to acquire that scan because you're getting more data. If you use a lower digitization frequency and sampling rate, or if you do more compression, you're going to acquire less data. So your acquisition rate would be a little bit faster in this case. So we'll talk about compression with phased array here coming up next. The top red colored waveform represents our original analog signal. Each green point represents the digital samples that will be acquired by our 100 megahertz digitization process. The scenario that I'm simulating here is using a 5 megahertz probe along with my 100 megahertz effective digitization frequency, which would result in a sampling rate of 20 samples per period, so the green dots. And for this example, I decided to simulate a compression of 1, which essentially means no compression. We are keeping every sample point acquired by the digitizer. The resulting digital waveform after compression, shown in blue on the bottom, is essentially drawn out by connecting the dots between samples, and in this case results in a digital representation that has excellent fidelity when compared to the original analog. For this one, I'm simulating a compression of 4. So again, that top red colored waveform represents our original analog signal. Each point represents the digital samples that were required by the 100 megahertz digitization process. I'm thinking of using a 5 megahertz probe along with my 100 megahertz digitization frequency, which would result in a sampling rate of 20 samples per period. And for this example, I decided to simulate a compression of 4, meaning that for every 4 samples, I'm most concerned with the greatest amplitude or most relevant sample within that group of 4. Those are represented by the green dots. The red dots represent the lower amplitude samples within each group. During our smart compression process, only the most relevant sample from each group will be preserved, along with its amplitude information. The green ones are the most relevant or highest amplitude. The lower amplitude samples, the red ones, will be discarded. Note that there is not an equal spacing between each green sample point that we keep. So in order to maintain equal spacing between samples, the green ones will get repositioned to the location of the first one in the group. This is a process that I describe as keep the high, drop the lows, and reposition. The relevant samples are then plotted as seen on the bottom blue example. So for each group of 4, we kept the highest amplitude samples, so amplitude accuracy will always be preserved no matter what compression level I choose. But since we reposition the location of each sample, your measurement accuracy could start to degrade, especially when using too high of a compression. For the next example, I'm going to simulate a compression of 8, meaning that for every 8 samples, I'm most interested in the one with the greatest amplitude, or what we call the most relevant sample within that group of 8. Those will be represented by the green dots. The red dots represent the lower amplitude samples within each group. During our smart compression process, only the most relevant sample from each group will be preserved, along with its amplitude information. Those are the green ones. The lower amplitude samples, the red ones, will be discarded. So there's not always equal spacing between the green samples that we keep. So in order to maintain equal spacing on our compressed A scan, the green ones get repositioned to the location of the first one in that group. And again, I describe this process as keep the high, drop the low, reposition. Keep the high, drop the low, reposition. The relevant samples are then plotted as seen on that bottom blue example. And for each group of 8, we only kept the highest amplitude samples. So amplitude accuracy, will always be preserved no matter what compression level I choose. But since we reposition the location of those samples, your measurement accuracy will start to degrade, especially when you use more and more compression. This is a representation of a rectified compressed A scan. So I took this from the Evident book, Advances in Phased Array Ultrasonic Technology Application. And again, it shows a rectified A scan. I'm using a compression of 4 here, as I showed you on one of my previous RF examples. Due to this smart compression, as you can see, amplitude accuracy or amplitude fidelity will always be preserved, again, because we keep the highs and we drop the lows. So if your flaw acceptance and rejection criteria is purely amplitude based, well, in theory, you should never have an issue, no matter what level of compression that you choose to use. But what if you have to perform through-wall height sizing of your indications? For example, maybe using fracture mechanics acceptance criteria, crack sizing, that sort of stuff. Or what if you're performing a critical 0-degree job where you need to maintain a really tight margin of error on your depths and your thicknesses? It is possible that you may get in trouble if your compression goes too high. As you can see on these 2 A scans, the original on top and the compressed on the bottom, the one on the bottom has much lower resolution along the time base, much lower timing fidelity. And since we reposition each sample that we keep, remember, keep the high, drop the low, reposition, it is possible that our time of flight measurement accuracy could be compromised if we use too high of a compression, especially if you use a lower frequency probe with a longer wavelength. When we perform compression, we only keep and save the samples that are preserved at the end of the process. So if this example was using 100 megahertz digitizing frequency along with a 5 megahertz probe and doing a compression of 4, we would only keep a net digitizing frequency of 25 megahertz. So let's go back and look at the ASME requirement one more time. A-scan data shall be recorded for the area of interest in an unprocessed form with no thresholding at a minimum digitization rate of 5 times the probe frequency. Well, as already stated, when we perform compression or subsampling or scale factor, whatever you want to call it, we only save and record those points that were preserved after compression. And then that line about an unprocessed form, what do we consider processing? Keep the high, drop the low, reposition. That's a whole other conversation that could be had. I'm not going to go there right now, but it is something for you to ponder. So how do we interpret this? Well, here's the question at the heart of everything. I've got a few choices. A, do we satisfy this statement about 5 times the probe frequency if our instrument natively runs at 100 megahertz, no matter what your compression is? Or B, do we only satisfy this statement when our compression preserves a sampling rate of 5 times the probe frequency after compression when it's all said and done? In my experience, this is what I've seen. About 5% of the technicians in the industry agree with choice A. About 5% agree with choice B. The other 90% of the industry has no clue that this is even a thing. And that's why we're doing this video. In most cases, the choice between A and B above comes down to interpretation or a certain point of view, meaning whoever writes your procedure. A certain point of view?
So what I told you was true, from a certain point of view.
A certain point of view?
Luke, you're going to find that many of the truths we cling to depend greatly on our own point of view.
Many of the instruments on the market today automatically adjust your compression, aka scale factor or subsampling, in order to ensure that your resulting digitization frequency after compression is at least 5 times the probe frequency. The formula used is auto compression equals 100 megahertz, or whatever your native digitization frequency is, divided by 5 times the probe frequency. The points quantity refers to the number of samples of that original 100 megahertz digitization process that the software saves and displays along the A-scan. As the UT range is increased or decreased, the software will add or subtract points as necessary to maintain a consistent net digitizing frequency. This value represents the saved digitizing frequency achieved after performing your compression. If you take your effective digitization frequency, which in this case is 100 megahertz, and you divide it by your compression, you get your net digitizing frequency. So that is what you actually achieve after compression. The net digitizing frequency ideally should be greater than or equal to 5 times your probe frequency to ensure high A-scan resolution and optimized ASME compliance. But amplitude information will still be maintained even at lower settings. So if what you're doing is purely amplitude based, we have a safety net because the smart compression process always preserves amplitude information. Higher net digitizing frequencies and points quantities will take up more data file space and result in slower acquisition rates, but creates a more dynamic looking, higher resolution A-scan signal. And then lower net digitizing frequencies would have the opposite effect. And here's a few examples of what the auto compression feature might calculate for some common probe frequencies. If I'm using a 10 megahertz probe, 100 megahertz divided by 5 times 10 equals a compression of 2, resulting in a net of 50 megahertz. If I'm using a 7.5 megahertz probe, 100 divided by 5 times 7.5 equals a compression or scale factor or subsampling of 2.66, which would result in a net of 37.5. If I'm using a 5 megahertz probe, 100 megahertz divided by 5 times 5 equals a compression of 4, which would result in a net of 25 megahertz. And then if I'm using a 2.25 megahertz probe, 100 divided by 5 times 2.25 equals a compression of 8.9 and a net of 11.25 megahertz. You could work this out with different frequencies, but I just decided to use some of the more common ones. So now I want to show you a few examples of this in action on my OmniScan X3. And then after that, we'll talk about how to calculate this if your instrument does not automatically do it for you by manually calculating the points quantity. Okay, for the example here on my OmniScan X3, what I've done, I created a simple 40 to 70 degree sectorial shear wave with a 5L16 and an N60S 60 degree shear wave wedge. And I've not really made any changes to anything. I've got like a 1-inch range on my depth scale, and I haven't really adjusted too much. I didn't even adjust my filters. I'm leaving the video filter off just so we can see the A-scan resolution better. And I'm looking at a series of side drilled holes on your standard phased array resolution assessment block. So I'm looking at the small radius of holes on that block. So I just turned up my setup, and what the system has automatically done is this. The effective digitization frequency, that's the native digitizing frequency on your instrument, that's 100 megahertz, right? And I'm using a 5 megahertz probe. So 100 divided by 5 times 5 equals a compression of 4. So 100 divided by 5 times my probe frequency equals a compression of 4, which results in a net digitization frequency of 25 megahertz. And I'm on this basically a 1-inch range. And what I'm gonna do is actually just hop over to an A-scan view only. So I'm on a 1-inch range, and you can see that for this range, I needed 612 points in order to get the compression and really to get the net digitization frequency of 5 times my probe frequency. So remember this number, 612. Now what I'm going to do is just go through and I'm going to essentially double this range. So I'm going to put this range to 2 inches instead of 1 inch. Go down here to my advanced settings, and you can see the compression is still the same, the net is still the same, but in order to get there, since I doubled my range, the software had to double my points quantity. And I'm maintaining the same A-scan resolution, This A-scan looks the same. And if I go back and look to my A and my S view, yeah, it zoomed out a little bit. So if I wanted to really see this a little better here, I could just sort of zoom in, right? I've got the same resolution that I had before, because the instrument automatically calculated the number of points required to maintain the same compression and net when I change my range. And if I change the range again, let's say now that I go to say 4 inches, right? And I may have to zoom out and zoom back in because I've introduced a different range. But I'm maintaining the same exact resolution on this A-scan because the software is automatically calculating the additional points required in order to maintain the same compression. And 100 divided by 4 equals a net digitization frequency of 25 megahertz. So again, on newer versions of the OmniScan X3 software, like some of the other instruments out there, the instrument by default sets a compression and a points quantity that is necessary to maintain your net digitization frequency of, by default, it's 5 times the probe frequency. So what would happen if I change the compression? So I can go here, and if I put my compression on 1, okay? Well, a compression of 1, and I'm just going to show my A scan here. A compression of 1 essentially means a compression of none, right? So this would be all the available sample points that the digitizer was able to achieve with this 5 megahertz probe. And I'm getting roughly 20 samples per period here, because 100 divided by my 5 megahertz probe is basically telling me that I've got 20 samples per period, and I'm doing a compression of 1 means a compression of none, and I've got a net digitization frequency of 100 megahertz. And if I wanted to change my rectification, right, I've shown you a lot of stuff with an RF. So this would be a high resolution RF waveform, right, with no compression. And then as I change my compression, you'll see that the resolution eventually starts getting a little bit more blocky, a little bit more chunky, right? Because I'm saving fewer sample points, and my net digitization frequency is going down. And if I continue to change the compression, right? Compression of 3, look at that signal, right? It's sort of getting kind of blocky here, right? And the net digitizing frequency is decreasing. And if I go up to a compression of, say, a big number, I'm just going to pick 8. Look how poor the resolution is on that signal, right? So I would not want to be taking any sort of, trying to take any accurate depth or sound path measurements with a really highly compressed and low net digitizing frequency. Ideally, I would be using the highest digitization frequency that my instrument would allow for, but that could eventually slow your scan down, right? So the main goal with ASME, typically, you would want to make sure that your net equals 5 times your probe frequency. And yeah, that's not a perfect resolution A scan, but it's adequate enough for most of your ASME work. And the cool thing about this is you're never going to lose an amplitude no matter how much compression you use. So more compression gives you lower resolution on the time base, obviously, but let's watch this amplitude. I'm at 68%. I'm just going to change my compression to 1 to go back to no compression, and I'm still at 68%. And if I do a really high compression, right, I'm still at 68%. So no matter how much compression you use, your amplitude is always preserved because you keep the high, drop the low, reposition. But your A scan resolution will change. And if you go too high, this is basically telling me that I've got about 13 thousandths of an inch in between each one of our samples. Your measurement accuracy could start to change, especially if you're using especially like a low frequency probe with a really long wavelength. So the auto compression, 100 divided by 5 times your probe frequency. In this case, 100 divided by 5 times 5 is 4. And then again, 100 divided by the compression equals your net. Your net digitizing frequency for optimized ASME compliance and good signal quality, your net digitizing frequency should be at least 5 times your probe frequency. What I've done here, I'm using an older version of the OmniScan software where the points quantity was not automatically calculated for you. So I built a simple sectorial scan with my 5L16, just doing a 40 to 70 degree sweep. And I haven't made any changes here to any of the settings. By default, the old software used to put you at 568 points. So currently on this small 1-inch depth range that I set up, I've got really good resolution on the holes and on my A scan, right? You can see the different lobes here. This is not an uncompressed signal. It's slightly compressed, but I've still got a net of 5 times my probe frequency, basically just because I got lucky with the range and the number of points that I had. But this is the problem. This used to be the problem. What if I change my range? What if I doubled the range, right? Okay. Well, if I go look, that same 568 points quantity, now, since I stretched it out to a longer range, I've now got a higher compression level and a lower net digitization frequency. And if I were to zoom in on that hole, you'll see that the resolution, both on the sectorial scan and on the A scan, have suffered. And then if I increase that range even more, say like a really big number, like 5 inches, I've got to zoom out and basically zoom back in. And what we'll see is that on that larger range, that 5-inch range, I've got even more compression, and my A scan and sectorial signal has suffered greatly, right? It looks really pixelated, really blocky, really chunky. So that was the problem that we used to have on older versions of software and on previous instruments like the MX2. If you made an increase or a decrease in your range and you wanted to maintain the same A scan quality and resolution, you would need to calculate the number of points required to do so. So I'll show you how to do that in a couple seconds. We would see the same thing using a 0 degree. So now I've built a 0 degree linear with a 5L64, and I'm looking at a side drilled hole that's down about 0.4 inches or about 10 millimeters with the default points quantity of 568. I'm showing a compression of 2 and a net digitization frequency of 50 megahertz, which is really good. I've got a really high resolution signal here. So, you know, I'm in pretty good shape, but I'm only looking at like a 1-inch range, right? So what if I increase my range? What if I doubled it? What if I went to 2 inches? And I'm gonna have to zoom out and then zoom back in. Well, you'll notice that the resolution that I get on both my sectorial and my A scan, they've diminished, right? The resolution has diminished. Why? Because that 568 points spread out over a 2-inch range is not going to have the same resolution if it was only on a 1-inch range. My compression has now increased and my net digitization frequency has now decreased. And then if I take it even further and do a larger range, we'll just go to 5 real quick. And yeah, there's going to be a bunch of multiples on the screen from this wedge, but that's okay. I'm just mainly worried about our little side drilled hole signal up there, right? So a 5-inch range, the resolution has gotten even worse because again, those same 568 points spread out over that bigger range, I have more compression and now a lower net digitization frequency. If you had to calculate points quantity, if that was the way that you adjusted your A scan quality, any change in the UT range would also need to be accompanied by an adjustment in the points quantity. Thankfully, that's all cleared up in the modern instruments and software, but it was a thing in the past that we had to contend with. Not everybody really learned how to do it well or understood it well. And so I'm going to show you how to calculate this and get it right. Okay, so we have to state a goal. My goal here is to set a points quantity sufficient to achieve a net digitizing frequency of greater than or equal to 5 times my probe frequency, which would result in at least 5 points per period of a sampling rate. The Y here, that preserves our timing fidelity or accuracy to greater than 90%, and it limits timing error to less than or equal to 10% when comparing the original analog signal to the resulting digital. This also preserves an amplitude fidelity of greater than or equal to 80% and limits our error less than or equal to 20%, aka 2 dB. But since we're using the smart compression, amplitude info should never be jeopardized because we always keep the high, drop the low, and reposition. So what I need to know? I need to know my desired UT range. I need to know the frequency of the probe and the velocity of the material so I can also calculate the wavelength. So here's an example. I've got a 5-inch range, a 5 megahertz probe, and I'm running about a 0.232 inches per microsecond velocity. That would equal 127 millimeters, 5 megahertz, and about 5.89 millimeters per microsecond. And the reason I use millimeters per microsecond, it's easier to calculate the wavelength than if I was using meters per second, because I don't have to convert anything. I'm just all in microseconds. And then we're going to solve on the next page. So step one, the wavelength formula. If you're a UT person, a UT technician, that's the one formula everybody should know: velocity divided by frequency. So in this case, I divided those, and I got a wavelength of about 0.0464 inches, or about 1.18 millimeters. So now I need to figure out how many wavelengths are in my range. So I take the 5-inch range and divide it by my wavelength, and I get about 108 cycles or wavelengths present within that 5-inch range. Step three, take those number of cycles in your range and multiply it by the number of points that you want to achieve per period or wavelength. So in this case, 108 times 5 would be 540 points. Step four, multiply those 540 points by 2, because we have to account for the round trip pulse going out and then the returning echo when we do pulse echo, because we're recording on both paths. So 540 times 2 would give me a 1080 points quantity. So next we're going to go back to the OmniScan. We're going to plug that in and see what happens and see if we have success. Okay, so we're back on our OmniScan, and just to rehash, I'm still zoomed in, but we're now on a 5-inch range. And if I go down to the advanced tab, obviously that 568 points was not sufficient to get a net of 5 times the probe frequency. So just like we calculated a second ago, I'm going to enter that 1080 points quantity that we just calculated on the PowerPoint. And what do we get? Haha, there we go. I've got a net digitizing frequency of 5 times my probe frequency, right? So I had to calculate the number of points required to achieve that desirable net and compression. And every time you change your range on older softwares, including the older versions of the X3 and also the MX2, a range change should be accompanied by a points quantity calculation in order to achieve the same level of A-scan resolution. Next, I'll show you how to do this on an angle beam setup. Okay, so in order to do this, again, we've got to set a goal. This is how I teach it in class. The goal is to get a points quantity sufficient to achieve a net digitization frequency of at least 5 times my probe frequency, which would result in at least 5 points per period sampling rate. Why? We've already talked about why this is important. What I need to know, my desired UT range, and then I also need to know my frequency and velocity in order to calculate my wavelength. So for this example, we're going to use a 5-inch range, 5 megahertz probe, and a velocity of 0.1276 inches per microsecond. That's the shear wave velocity of carbon steel. That would equate to 127 millimeters range and about 3.24 millimeters per microsecond velocity in metric. The reason I use millimeters per microsecond is if I keep everything in microseconds and I have my frequency in megahertz, they wash out and it's just easier for me to calculate my wavelength. And then we're going to look on the next page and see how to solve it. So again, step one would be figuring out my wavelength. So V over F, and I get about 0.02552 inches, or about 0.65 millimeters. And the reason I go out to so many more decimal places, the more decimal places, the more accuracy you get in your final answer. So how many wavelengths are in that range? Well, 5-inch range divided by that wavelength, and I'm going to get about 195.9 or 196 cycles in that range. Step three, I take that 196 cycles and I multiply it by 5 points per wavelength, and that gives me 980 points. Okay, step four, we've got to take those 980 points and multiply it by 2 in order to account for the round trip of that pulse echo path going out and coming back in. So 980 times 2 would be 1,960 points. Okay, step 5, let's plug it in and see what happens. See if we have success. Okay, so what I've got is a sectorial scan that I created with my 5L16. And I'm at the default settings here of that 568 points, which gives me a compression of 19 in this case, with only a net digitization frequency of 5 megahertz. And I set the range to equal 5 inches on my 40-degree angle. So I set up a true depth range, right, on the OmniScan. Every angle has the same sound path going out, but the low angles will see deeper than the high angles will. And this is called a true depth range. So I put my, on my 40, I put my range at 5 inches, and I'm just putting an angle into this side drilled hole and zooming into it just so we can see the resolution, right? Really poor resolution, okay? So let's do the calculation that we just talked about. I'm going to verify here that my range is 5 inches because I'm going to do all my math based on this 40 in a few minutes. So we're going to go down and look at the points quantity, right? That 568 points quantity obviously was not sufficient to give me the net that I was looking for. And what we just calculated on the slide was 1,960 points. Let's see what that does. Does it work or not? Well, we got an improvement in our compression and a higher net digitization frequency, but we did not get our goal that we stated. We did not achieve our net of 5 times the probe frequency. And if I zoom back into that hole, right, we've got better resolution than we had a moment ago, but we still don't have great resolution. And we certainly don't have resolution enough to reflect a net of 5 times our probe frequency. So what happened? Well, let's go back to the drawing board. So we did not achieve success in that round. Let's think about why, okay? The range that was showed on the Omni was based on depth, but we need to actually convert it to sound path because that is the true A-scan path, the A-scan range that's being calculated. So the old school shear wave formula for calculating depth was sound path times cosine of the refracted angle equals your depth. If you wanted to rearrange that, we could say sound path equals depth divided by cosine of the refracted angle. So the reason we do this, with shear wave, typically we know the sound path and the angle, and we're doing trig to calculate the depth. Well, in this case, I know the depth. That was my true depth range. And I know my angle, so I just need to figure out my sound path. So I'm going to enter my numbers in. I had a 5-inch range, depth range, which I'm going to divide by cosine of 40. And that's going to tell me the sound path was actually equal to 6.527. So for that 40-degree angle to go down 5 inches, it had a 6.527-inch sound path range. So you could pick whatever angle you wanted to, just make sure that you use the depth that's associated with it. So I'm going to redo step 2 from the previous page with that sound path range. 6.5 divided by 0.02552 gave me about 255.7 cycles or wavelengths present within that range. I'm just going to round it up. 256 cycles times 5 points per wavelength equals 1,280 points. If I multiply that 1280 by 2 to account for both paths of pulse and echo, that gives me a calculated points quantity of 2,560. So now we're going to plug that in and see if we have success. All right, so we're going to plug in that points quantity that we calculated, 2,560, because we're now accounting for the angled sound path as opposed to just the depth. So what do we get? Success. We've got a net of 5 times the probe frequency, and this is going to be adequate resolution for most codes, most ASME stuff, most of your procedures. It's not so much the instrument's digitization frequency, right? We're only recording the net. And it is way more preferable if the software calculates this versus us having to do it ourselves, because as you can see, it's kind of a long process that most people never learn or never have the time or desire to do. Okay, so really quickly, I wanted to show you the same thing on a previous generation hardware. So I'm using my OmniScan SX, which is, sort of a mini version of the old MX2. So I'm looking at the same 0-degree setup with my 5L64 and looking at that same 0.4 deep hole, about 10 millimeters deep. And initially I've got a 1-inch screen range here. And if I go look at the Advanced tab, you've got points quantity and scale factor. So scale factor is equivalent to the compression readout that you have on your X3. And notice that that's grayed out. You can't actually make any adjustments to that. So what the software used to give you, you could pick 160, which is giving me a low resolution signal and a lot of compression, or I could choose 320, which is giving me a better resolution and a lower scale factor, or I could choose 640. So these were some of the defaults, right? And as I increased that, my scale factor got small and my resolution got better. There was an auto function here, but it would not automatically give you a net of 5 times the probe frequency. In this case, it's doing really well because I've got a very small UT range. So the auto on the MX2 and the SX was basically designed to give you a good compromise between signal quality and scanning speed, but it did not perform the same auto that we've already discussed with the X3 and the Topaz, the newer generation instruments, right? So what if I changed my UT range? And I'm going to change it to 5 inches. Okay, so just like I did on the X3 before, if we go to the Advanced tab, you can see obviously that now I've got a scale factor or a compression of 7, which was not going to be good enough to meet the goals that we've already discussed. So what we calculated earlier for the 0-degree would be entering a points quantity of 1080. Oops, 1080. So this should give me a scale factor of 4, which would be equal to a compression of 4. You see that? Got a scale factor of 4. So this instrument also runs at 100 megahertz. So if I take 100 megahertz and divide it by 4, there's no net digitizing frequency readout on the MX2 or on the SX, but I know that this works because of what we've already discussed. Okay, so now I've made an angle beam setup similar to what we did earlier, and the default was 320 points, and I'm showing a scale factor of 7, and I've got a around a 1-inch UT range that I've got configured. And you can see that when I was zoomed into that signal, I mean, it had decent resolution, but not great resolution, again, because that scale factor of 7 is equal to a compression of 7, right? And if I went through and changed the points quantity, my choices are 160, and you can see I've got a low resolution signal with a high scale factor or high compression, 13 in this case. And if I go to a 640, I've got a better resolution signal with a lower scale factor, a lower compression, right? And then there's also the auto, but the auto doesn't always perfectly give you exactly what you want. In this case, since I've got a very small range, I'm doing pretty good. But what if I increase my range? So I'm going to go back down to my 40 real quick. Because that's the math that we did on the slideshow. So on my 40, I'm going to add a 5-inch range, right? A really, really big range. And if I put my angle into that side drilled hole, well, you can see now, since I've increased so much range, that I've got a scale factor of 16 at auto. That would be a compression of 16. So we're talking about a very low net digitizing frequency. And again, 160 would be even worse. I mean, look how bad that signal is, how pixelated that is, right? That's a compression of 64, which is pretty substantial. 320, I got a scale factor or compression of 32. 640, I've got a scale factor or compression of 16. None of these are really giving me the resolution that I was seeking for, the scale factor or compression that would lead to a net of 5 times my probe frequency. So the number that we calculated on our points quantity earlier, in order to get that compression of 4, which would have gave us a net of 25 megahertz, the number that we calculated earlier was 2,560. So if I type in 2,560, and before I hit enter, let's see our acquisition rate right now. That's our scanning speed. That's about 60 hertz or 60 millimeters per second. Let's see what happens when I add this really big points quantity. Okay, well, notice that my acquisition rate slowed down a little bit, but I got the number that I was looking for here. I got a compression or scale factor of 4. 100 divided by 4 would have given me a net digitization frequency of 5 times my probe frequency. And I've got the adequate resolution back. And that's how you do it. So that's a lot, huh? The compression and points quantity subject has been one of misunderstanding and even contention in our industry over the years. It wasn't always taught or understood thoroughly, but now it is. Thankfully, most of the current generation instruments, now they have a pretty user-friendly automatic calculation on board to help us maintain quality A scans and optimize code compliance. But that's not always been the case, as you can see. And I'm not here to say that any incorporation or lack thereof of these parameters in your procedures is right or wrong or code compliant or not. Over the years, my opinions on this matter have changed as my knowledge and experience has improved. So my goal here is to help you do the same thing. Everybody will interpret these items differently, and there's still a little bit of gray area in the codes that I think could probably be clarified. My original goal was to show you how to do this on all the major instruments on the market today, but A, I don't have all of them at my disposal, and B, as you can see, this has been a pretty lengthy endeavor as it is. So maybe one day I can do a follow-up with different instruments. The next and final episode in this series will deal with TFM grid resolution and amplitude fidelity. That's actually been my end game with this series, but I felt the need to put the building blocks in place first. So stay tuned for that. If you find this information informative, please like, share, and subscribe, as your support helps me to continue doing this. Take care, and we'll catch up real soon.